So hopefully, after today's lecture, you will have a sense of how a deep neural network can be used to generate novel and realistic images through two methods, mainly autoencoders and generative adversarial networks. Lastly, we will see a very interesting phenomenon, that is how to make convolutional neural networks misclassify images by making only very small changes to the images. So we've covered a lot of techniques previously for solving vision problems with deep learning. We mainly focused on supervised learning techniques, where we have the data and there are ground truth that could either be a label or some other data structure like bounding boxes or semantic maps. And we first saw how to treat a convolutional neural network to perform generic image classification by predicting one of many labels by applying a cross-entropy loss function, which can be extended to predict multiple keywords for an image. So we can tag an image with different properties by replacing the softmax with a sigmoid. Then we moved to more elaborate techniques, and so how to formulate object detection so that it can be solved through end-to-end deep learning and training in an attempt to localize objects within an image so that we can find their class and find a bounding box that encloses them. And then in the last lecture, we saw how to do this classification at the pixel level, so we can assign a class label to every pixel in the image. And today, this is, in general, a very common procedure for all these tasks. So we first pick a neural network. It could be something pre-trained on ImageNet, like VGG or ResNet. We design an encoding for our output, how we want our output to be structured. And then we pick an appropriate loss that can characterize how well the network is doing during training. And then we trained our network. And if we do this, we end up with a machine that can do really good pattern recognition. This is all very good and well, and works very well, especially if we have lots of data. But what can we do if we do not have labeled data? Then we have to move to techniques that involve unsupervised learning. So the objective in this lecture is to see how we can use deep learning in an unsupervised learning way. So when we don't have labels or target class, what can we do in these cases? And the goal instead is to find out properties of the structure of the data, which we can then use to generate new data or to identify if points belong to a similar distribution. So overall, the goal in this unsupervised learning is to understand the hidden underlying structure in the data. And we previously saw methods like k-means and PCA that have similar ideas. And today we will try to tackle similar problems with the use of deep learning. But first, let's talk a bit about why do we need these so-called generative models. First of all, we have to understand some of the limitations of discriminative models. So they have a number of limitations, like, for example, they cannot model the distribution of the underlying data. So we don't have a way of seeing, of understanding how probable is an image. to be generated from a distribution. And we cannot sample from that distribution to generate new images. And these are the two tasks that we'll see today. So we want to use generative modeling approaches for these two reasons. The first two has to do with the concept of a density estimation to see, basically, when we see a bunch of samples, we want to learn a model that approximates the underlying distribution, so where these data are generated from. And the other task is this idea of new sample generation. So when we're given input samples, we want to train a model to be able to generate brand new samples that look similar and come from the same distribution as our input data. So the core question behind generative modeling is how do we model these probability distributions and how do we find it so that it is similar to the true distribution that describes how the data was generated. And some of the uses of these generative models have to do with their capability of uncovering underlying features in the dataset. So, for example, if we have a phase detection problem, where we might be given a dataset with many different phases, and we may not know, for example, the exact distribution of phases in terms of different features like skin color, gender, or the pose of the face. So our data can end up having a lot of biases, so having a lot of some features and less than other features. And when we do this, our model will end up having the same biases. So with generative models, we can uncover these underrepresented parts of the data, and we can use this information to create fairer and more representative data sets. Another great example of using generative models is for finding outliers. So for instance, if we have self-driving cars application, most of the data that these cars collect might be from very common driving situations like driving down straight roads or the highway. But it's really critical for a self-driving car to be able to operate in situations that might be a bit unfamiliar. So for example, when we have bad weather or a pedestrian jumps in front of the car. So these are the corner cases. So generative models can be used to detect these outliers and train more robust models. So given the training data, we want to figure out how to generate new samples that belong to the same distribution as our input data. So we want to find a generating function that gets a latent variable and then generates a new data point. And so we'll see in a bit more detail two classes of models that we call latent variable models that do exactly this process. But first, let's start with what is a latent variable. And this is in contrast to observable variables. So observable variables, as the name suggests, are variables that we can directly observe through a model. Latent variables, on the other hand, we cannot observe them directly, but they are what captures the actual underlying representation of the data. So latent variable models attempt to describe the data through latent variables. And the benefit of using these latent variables is that they could be they could occupy a lower dimensional space, and in that way they are easiest to process, and they form a more compressed representation of the data. So in the case of images, that can be very high dimensional. So what we want to do is take the image and encode it in a latent variable, which has a compressed smaller vector form. So let's start by first discussing a very simple generating model that tries to do this encoding of its input, and it's called Autoencoder. So to take a look at how an autoencoder works, we first begin by feeding raw input data into that encoder, which could be a series of neural network layers that we have seen before, like convolutional layers or fully connected layers. And we feed that through an encoder network. And what is outputted at the other end of that encoding is a representation of what is learned in a lower dimensional space, which is the latent space, which we denote with a symbol Z. This is the feature representation that we're trying to predict, actually. But the problem is, how do we actually train this such an encoder? We don't have in our training data a label that corresponds to the vector Z. And the answer is we don't need to have this representation. We only have to use the data itself. So we can get around this problem that we don't have any supervising signal or label by building a decoder structure that is used to reconstruct a resemblance of the input image from this learned latent space Z. Again, this decoder is a series of neural network layers, as we saw in semantic segmentation, where we have this upsampling or the convolutional layers that project back into the original image space. So in this way, we train a network like this by using the input itself as the ground truth and the mean squared error as the reconstruction loss, which basically checks for every pixel if the value is close to the input image. So this idea of unsupervised learning is a powerful idea. And this allows us to quantify these latent variables that we're interested in, but we cannot observe. So a key consideration here is this dimension of the latent variable, which basically represents the dimensionality that we project our data. As it is a form of compression, as you can imagine, the lower the dimensionality of this latent vector, of this latent variable, then the reconstruction would be a bit poor. So as you can see in this example with a mixed dataset, you can see that if we have, for example, a two-dimensional latent space, we get some really fuzzy images, but as we increase it to 5, the representation gets much better. So this is where the name autoencoder comes from. So basically, it's a method for automatically encoding our data using this reconstruction loss that forces the latent representation to capture and summarize the data into this hidden bottleneck layer that basically is our representation in a compressed form. So this form of autoencoder can be extended further into what is called a denoising autoencoder. It's really similar to what we had before, so this encoding and decoding structure. But the difference is that we, instead of inputting the original image, we now add some noise to that image. And this adds the following advantage. So basically, if we add these small perturbations to the data, it can make it more robust in the reconstruction. So the main idea is that higher level representations or more compressed representations are relatively stable and robust to the corruption of the input. So if we do that to this type of autoencoder, the autoencoder will learn to capture more meaningful, more useful structure from the distribution of our input. In other words, this denoising is a training criterion for learning to extract useful features that will lead to a better, higher level representation of the input. So what the traditional autoencoder does is that it goes from the input to a reconstructed output, and it tries to do that as best as possible. So guided by this reconstruction loss, which is basically a mean squared error loss. But if we want to learn a more smooth representation and basically make that latent space so that it's is close to a distribution, it approximates a distribution, and generate data from that distribution, then we need a structure that is called a variational autoencoder. So it's this idea of, again, uses the same principles of an autoencoder, but it adds this generative aspect to it, so that it maps the data into a distribution, which we can then sample to generate new data. So what we are changing in the original autoencoder is this is the bottleneck layer. We replace it with a stochastic sampling operation. So instead of learning latent variables, as we did before, we learn a vector of parameters like a mean and a standard deviation that describe a probability distribution that is associated with those latent variables. Then what we can do is to sample from these distributions to obtain a sample from that latent space. So in essence, the variational autoencoder is just an autoencoder, but it has this probabilistic twist instead of the more traditional bottleneck layer. So if we do that, both the encoder and decoder are now probabilistic in nature. So what the encoder does now is compute the probability distribution of the latent space given the input image, while the decoder is doing the reverse inference. It's trying to compute a new probability distribution of the input given the latent vector. And because we introduced this probabilistic aspect to the network, our loss function also has to change. It still has the reconstruction component, but with the L2 loss for pixel-wise difference. But we also introduce another component in the loss. We introduce this regularization term D, which it basically acts as a regularizer to make sure that what the encoder does, what the encoder computes, is actually a distribution and that it resembles the distribution that we want to. And the way it's done is, but we basically add a prior to the distribution we want to model. So we say beforehand that in the encoder, the distribution we want to form is, for example, the Gaussian distribution. So this prior helps by placing an initial guess on what the distribution might be. So if we enforce this latent variable distribution to follow that prior, we can help the network learn better. In other words, we help the network not overfit, because without it, the network could probably learn to overfit in some parts of the latent space, because we don't have any structure in that latent space. But now, by enforcing it, it has to make it similar to the distribution we are using as a prior. So this smooths out the latent space and the learn distributions. And now, specifically about this regularization term, is basically what is known as the callback liberal divergence, which is a measure of how a probability distribution is different from a reference distribution. And it's given in general by this equation here. And it's not an associative measure. So it's going to give you a different result if you swap the two distributions. But it captures the divergence between the inferred distribution, which is what the encoder does, and the fixed prior that we have placed. And the typical choice of this prior is usually a Gaussian distribution, which forces the encoder to distribute out evenly the encodings in the latent space. And the effect it does is that if the points are not evenly distributed, as you see in the image here, then they will form a different form of a distribution. And then the network will get penalized, so the loss will go up. So it gives a feedback to the network to spread out this, the latent space. Now for Gaussians, if we pick a Gaussian, for example, to have a zero mean and standard deviation of 1, the divergence loss takes a much simpler form, in the form of the mean squared error.
Christos, lost your voice in the last slide.
Where were we in this slide?
Yes.
Okay, so here basically what we see is the in this closer look at this regularization term. This is the callback Libler divergence, as it is known, and it measures how two distributions are different from each other. So if we use this with our prior, then we can see if the encoder learns to map the latent space in that distribution. So if, for example, we assume that we have a Gaussian, we expect the encoder to have this nice, evenly smoothed out form of the latent space. In other words, if it starts putting latent variables by focusing on one part of the space, then it will get penalized because that will not be the prior distribution that we selected, which is the Gaussian. And this is achieved through this KL divergence term. So one thing to consider here is that a neural network is a deterministic algorithm. So it translates an input to an output and does the same thing every time. So how do we actually turn this into a probability distribution? So we can do this by taking the output of the network. So we assume that it outputs the parameters of the distribution, and then we can use those parameters to sample from a multivariate normal, for example. So now we have made a selection of prior. The autoencoder will take that form, and the encoder will compute these parameters for the normal distribution. And using those, we can sample a vector from the latent space, which the decoder can use to learn to reconstruct the input. If we have, if the dimensionality of our output is large, then we can often take this diagonal matrix, the covariance matrix of the multivariate Gaussian, to be diagonal, so it reduces our number of parameters that we have to estimate. So now we have defined the main components of the variational autoencoder. And we talked about how we can add the KL divergence into the loss function to basically force our learned distribution to follow the prior. We need to talk about the potential problem that this whole process has introduced. So we first pass the input through the encoder to obtain the distribution parameters. And then we need to sample from the distribution with those parameters. However, this is a stochastic process. There's this sampling process does not have a derivative, so we cannot backpropagate using stochastic gradient descent and backpropagation. So this needs to be deterministic if we want to apply the same way of learning as we did before with gradients in the chain rule. To tackle this, a breakthrough idea that enabled the variational autoencoders to take off and make the application of backpropagation possible was this reparameterization trick. The key idea in this trick is that we do not directly draw this latent vector from a Gaussian distribution, but we consider this sampled vector as a sum of the fixed vector mu, which is the mean of our of the Gaussian we are estimating, the fixed vector for the variance, and then we scale these variance by a random factor epsilon, which is where the stochasticity now goes. And that actually is drawn from a normal Gaussian distribution. The key idea here is that we still have this stochastic process, but we have decoupled it from the encoding part. So it does not directly occur in the bottleneck layer. So a better way to think about this, so you can understand it, is through this visualization here. So we have the deterministic nodes and the stochastic nodes. So as we saw, doing this backpropagation through the sampling layer is not possible because the sampling layer doesn't have a derivative. We just draw random data from a distribution. So instead of this, in this reparameterization form, we essentially divert the sampling step to the side, so we can still have a path from the encoder to the decoder. And this is what allows the variational autoencoders to be trained in an end-to-end fashion. So now we can backpropagate the derivatives through this Z layer, whilst before we could not. So training time we pass the input through the encoder to obtain the mean and the standard deviation vectors. Then we sample for the epsilon and generate our latent variable that we pass through the decoder to obtain the reconstructed image. And we optimize this through the loss that has both the reconstruction error, the reconstruction loss, which is the mean squared error, basically, and the KL divergence that tries to match the two distributions. So because now we have this sampling step in the autoencoder, by just sampling from a normal distribution, we can then use the decoder network that after the learning to form a generative model that is able to create new data similar to the observations that we had during the training process. So we will basically sample the prior distribution, which we assume follows a unit Gaussian distribution, and that vector we can use it to pass it through the encoder. We normalize the output and we get a new image. And now that we have this generation process, we can start doing a bit more exploration on this these drawn latent variables. So we can sample from this distribution and start to only change one of the variables in that vector and fix all the others. So we can slightly start tuning that variable. So we start from a low value and increase it. And we will see an intuition into what that particular variable within the vector contributes towards the generation process, and how the network builds an interpretation of the data. So by finding out what each variable does, we can then have a more targeted generation process. So in this example that you see right here, in these phases, they are a result of distorting only one variable in the vector. So in this particular case, that component affects the orientation or the pose of the face. In similar fashion, different dimensions of the latent vector can affect different properties. So ideally, we would want each of our variables to be independent and uncorrelated with each other. And in that way, they can learn the most compact and rich representation possible. So as an example, consider here again these mnist digits that are generated from a generation network. For 100 rigid digits, we could have, for example, one parameter, one property to be the width of the digit, the angle of the digit, or the thickness of the digit. So one can go and specifically design an image that has the specific properties that we want. And this idea of having these variables that each one contributes to one feature is called disentanglement. And in the variational autoencoder formulations, there are some that can enforce this by playing around with the loss function, basically, so that they make the latent vectors and their variables independent. Now, let's consider how we can use a generation model to help us in case of when we have underrepresentations in the dataset or an imbalanced dataset. Let's start by considering a standard classifier that could be trained, for example, on the dataset on the left. If we test it on the dataset on the right, we can say with confidence that it's going to do a poor job because the datasets, the distributions are not similar. We can take advantage of the variational autoencoder as a generative model, the decoding part, to discover which parts of the feature space are over or under represented. So we do this by first considering that a variational autoencoder can be trained to learn the underlying features for a given dataset. And as you can see, the variational autoencoder is built with this internal latent representation that controls, for example, here the face orientation. So it learned this head pose that is an important feature by the dataset. So now from these latent distributions that encode particular features of our dataset, we can estimate the distributions of these features. So in certain instances, for example, of people with glasses, this feature could be underrepresented or overrepresented. And if our data has many images of a certain overrepresentation, of overrepresented feature, the likelihood of selecting this type of image will be high. So what we want to do is to basically change this distribution to be more adaptive and to be able to resample features in the dataset that are underrepresented, and at the same time make features that are overrepresented not being selected that often. And then once we do that for the features, then that the decoder has learned, the encoder has learned, sorry, and we sample in that way, we can use this to generate a more balanced and data set, which will lead to a much more improved and less biased classifier. So in summary, the variational autoencoders encode basically a compressed representation of the input data that we can then sample to obtain reconstructions of data that belong to the same family. We can use this reparameterization trick to train our network in an end-to-end way, so that we are now able to do the backpropagation. And it has also these interesting properties that the latent variables can be interpreted, each of its components, by traversing their own space and obtaining an understanding of what each of these variables does and how it changes the generation process. And then we can do some targeted sampling from that learned distribution. And here you can see some faces generated from a variational autoencoder. Now, as you can see, some of the faces have, the features are may not be symmetrical, and it's kind of blurry, the images, but it gives you an understanding of what's the capabilities of this algorithm. Now, comparing together autoencoders and variational autoencoders, autoencoders are more focused on learning a compressed representation of the data. On the other hand, variational autoencoders, they learn parameters for a probability distribution that describes the data. So this is the main difference between the two. One is just a reduced representation. The other one also tries to find a distribution or match a distribution to describe the data. So since the variational autoencoder learns a model of the data, we can sample randomly from that distribution that it has learned, and then this leads to generating new novel images. And if you look at the examples of generated data, you can see that the autoencoder doesn't do a good job in generating new images, while the variational autoencoder is able to produce much more variety of data. So in both encoder and the variational form, what is learned and what is the main problem is this dense probability or dense data representation. And this is one form of tackling the problem. There's also just the approach that we are not interested in mapping the data into not only mapping the data into a lower dimensional space or distribution, but what happens if we just want to generate new data? And this is something that requires a different set of algorithms, but they rely on similar principles.